Hello and welcome back everyone to Foundation Engineering class. We will try to continue the class. We are on the chapter number 5 and this time we will go for the improved equation for elastic settlement. In the previous video we talked about settlement based on the theory of elasticity, okay? So the equation we did in this part number 3 are like being improved in this what we are doing now, the improvement of this equation, theory of elasticity, okay? So this is these two are like a little bit related, so I recommend you see the part 3 first before continuing with this one, okay? So number 4, then improved equation for elastic settlement. So this is a reminder of what we did in the previous lesson. Okay, we saw 3 equations for three possibility, 3 configuration of foundation. Okay, this first case is when the foundation is based on like this kind of soil, and the foundation is on the surface. Okay, surface footing, and this second one is when we have a rigid layer beneath foundation at the depth edge, but still surface footing. The third one is with embedded footing under, and under that footing we have a rigid layer. Okay, so anyway, for each case we had one equation, and we talked about how to obtain all the parameters in these equations. Okay, but the thing that is interesting here, we need to focus on here, is that in all these 3 equations, we have the elastic modulus, ES. You can see it here, ES, ES. And in the previous lesson, we said that the elastic modulus can be considered as like a average. The averaging method is this one, okay? Because it's difficult to have a uniform soil when you are dealing with an actual project, an actual construction site, okay? So for that, it was suggested to use an average modulus of elasticity, okay? But using average is actually not reflecting the reality of the soil. That's why we need to modify these equations to take account the fact that the modulus of elasticity is really not constant in the ground. Because if you go, the modulus of elasticity is like increasing when you go deeper in the ground. So how to consider that in the estimation of the settlement? Okay, so this is what we need to see in this section. This was section number 3, and let's go now for section number 4. So improved equation for elastic settlement. Okay, so in 1999, these people developed an equation for elastic settlement to consider the following thing: the foundation rigidity. Because if you remember in the previous lesson, we talked about flexible and rigid foundation. Okay, so the rigidity of the foundation is considered in the new formula. The embedment depth is considered. The increase of soil stiffness, the elastic modulus, the modulus of elasticity of the soil with depth, and the rigid layer below the foundation. So in this case, they did it for circular footing. So if you are dealing with a rectangular foundation, you have to use an equivalent diameter, okay? And we will see how to obtain the B equivalent now. is obtained from this equation. It means when you have a your footing shape, the shape of your footing is rectangle or square footing, you have to use this, you have to obtain B equivalent using this equation. Okay, so what is B? B is normally the width of the foundation, L is the length. So you already know if you are dealing with square footing, B and L are the same. Okay, for circular foundation, you don't need B equivalent. The B, you just use the diameter of the foundation. Okay, so here is an example. You can see we have a footing here. This footing, you can see EF. EF is the modulus of the footing itself. Is it a rigid footing? Is it a flexible footing? The E of the footing will tell us. The modulus of elasticity of the footing can tell us. Okay, so if you include that in the equation, okay, this rigidity of footing can be included in the new equation. Imagine we have equation that will consider all this. This is the rigidity of the foundation. And you can see that the foundation is embedded, DF, okay? And you can see a layer here, okay? So this figure is showing foundation B, B equivalent, the equivalent diameter, BE, embedment, DF, thickness of the footing with a modulus of EF. You can see here, the footing is here with thickness T and the elastic modulus of elasticity of footing is EF. Okay, and you can see also that we have a rigid layer beneath at the depth H beneath the footing base. Okay, you can see also that the soil here, the soil between the footing base and the rigid layer, this soil, it the thickness, the stiffness, sorry, the stiffness, this means the elasticity of this soil is increasing. It is not constant. You can see this line. The slope of the line is maybe K, like this. So ES is not a constant. It is increasing when you go deeper. Okay? So maybe if you go at the surface, it will become like 0 here. Yeah. Because we start here from the base of uh, the foundation. Since this soil is the one that is being compressed. Okay? So this line is showing the variation of the elasticity, the modulus of elasticity of the soil. It means the stiffness of the soil, which is increasing. Okay, so that can be given by this equation, the ES, the modulus of elasticity of the soil. The E0 means the modulus at this depth, at the base, at this level. Okay, then after that it increase like following this line. So depending on the K, depending on the type of soil, the K, it means the slope of this line can change. It can be this way or this. It depends. Okay. But what we want now to summarize everything, we want a very good equation formula that can consider all these. It will consider the rigidity of the footing, which means EF and T. It will consider the embedment of the footing. It will consider the presence, the availability of rigid layer under the footing, if there is a rigid layer or not. It will consider the fact that the soil stiffness is not constant, it increasing when you go deeper. If we can have an equation that take account all this, it will be very good. And this is the objective here. So remember that we need this, okay, the equivalent diameter. Okay, so I